So, hello everybody. Before we start, just a kind reminder regarding the quiz. So, in order to be able to submit a LabCom B1, you need to pass the quiz. This means that you mean to have at least 70% of the full mark of the quiz in order to be able to submit the LabCom B1. And the deadline of this lab is this Thursday. So be careful that you go through the quiz, you submit the quiz and you pass it before this Thursday. And now I think we can start. So last week we talked about mainly about the network layer and the MAC layer. Today we will go through the transport layer and we'll describe and explain the interface between the application layer and the transport layer. And in the end, we'll see together some performance aspects of computer networking. Port numbers. So if you remember, the port number is used by the transport layer to identify, to distinguish between the applications that are using its service. So above the transport layer, we might have many applications requesting this communication service at the same time. And when the transport layer receives a packet, it needs to know where to dispatch this packet. So this packet belongs to which application above the transport layer. So it uses the port number. So it uses the destination port number in order to know to which application it should dispatch the packet. To understand this better, let us consider this example. Here we have a host with IP address A, another host with IP address B. They are communicating together through the network. So on host A, we have many applications that are running at the same time and using the communication service provided by the transport layer. Some of them is using UDP, others are using TCP. On the other side, we have the same thing. So applications using TCP and others using UDP. We have process PA is sending a packet to process PB. Now, the process PA has a port number. The port number of this process is 1267. So when UDP receive a data from this process, so it takes the data. Here we can see the application data in the bottom, but it adds its own header to this data. So it adds what we call the UDP header. Within this header, we find the UDP source port and the UDP destination port. So the source port is the port that is associated with the application sending this data, and the destination port is the port assigned to the application that will receive this data. And above this, and above the UDP header, we have the IP header that will be added by IP layer. Inside this IP header, we find, as we mentioned last week, we find the IP source address, which corresponds to address A, and the IP destination address, which corresponds to B. And now, the packet receives to this host B. So the UDP is able to know to which application to dispatch this packet based on the destination port number. So in this case, it is 53. So it knows now that this packet should be delivered to process PB. And now, using the information that we have in this header, process PB is able to reply to the process PA because it will find the port number of this application and the IP address in that packet. Now, to understand the communication that we have in TCP/IP networking, actually, we talk a lot about client-server communication. And the term server is used to mean many things in different contexts. But in our context, we have a formal definition for that. And we need to agree on this definition before going forward, talking about the client-server communication. So what do you think? Which one of these 5 definitions fit to the meaning of server in our context? I will close the poll in 5 seconds. I close the poll, and the majority answered for the option 1, which is wrong, unfortunately. The correct answer is 4. Why? Actually, in our context, the server is any piece of software that is listening on a given port, waiting to serve incoming request. So this is why it is called a server. A server serves incoming requests, and is all the time waiting, listening on a given port to receive requests, to process them and to serve them. This is the difference between a server and a client. So a server is all the time is listening on a given port. The client does not need to be running all the time. And this piece of software is it's called server regardless the size of the machine where where this software is running. So it might be running on your smartphone, it might be running on a very huge machine in some data center. So, and also it's called server regardless the place where this machine is placed. It might be at your home, just simply your laptop, or maybe somewhere in the cloud. So again, a server is a piece of software listening on a given port, on a well-specified port for incoming requests to serve them. Now, let us move to the client-server computing. So the server on one side is always running, waiting to receive requests to serve them. The client, it should initiate, so the client initiates the communication with the server. So the client does not expect to receive something from the server, because the server is not necessarily aware about the client. So the client, when it needs something from the server, it needs to send a request, and then either this request just simple data and does not expect to receive anything, or it might request some data in case of a web browser or a web server. So your browser will send a request to receive some data, and the server will process your request and replies with the data that are required. So the client that initiates the communication need to be aware about the IP address of the server and the port number of the server. Otherwise, it cannot be communicated with the server. Now, some known applications use well-known port number by default. For example, if we take the DNS server is the one that's responsible of resolving the IP address in case you know the name of the machine. So the DNS server by default is listening on port 53. So all what we need to know now is the IP address of the server, and then you send a request, a DNS request to the server on port 53, and you get the reply. And also, again, the default port for HTTP protocols is 80. The default port for HTTPS is 443, and SSH is 22. So for these applications in general, all what you need to do is to resolve the IP address, and then you send your request to the corresponding port that's used by default. And again, so the server should be running in order to allow the client to establish or to initiate the communication with the server. If the server is not running, is not listening on its port, on its associated port, the client cannot communicate with the server. It will send a request, but the request will go nowhere. There's nobody to receive this request, and will be simply discarded. Now, as mentioned last week, the UDP service is message oriented. So what happens when the data has some message, when the application has some data to send using UDP? So it delivers the data to UDP. UDP put this data within a UDP datagram, so it does not change anything. It does not segment the data, does not apply any fragmentation on this data. Just it sends the data as it is to the other endpoint. It's not reliable. This means that if there is a loss in the network, UDP does not do anything to recover this loss. And if the application cares about this loss, it is up to the application to handle this loss in case it needs that. And also one message, so the maximum message size that can be handled by UDP is up to 64 kilobytes. This is the maximum message size. So, but this message cannot necessarily, it's not be able necessarily to go through the network. So this message is too big actually. And sometimes the MAC layer accepts up to only 1,500 bytes. So what happens in this case? So this message is put within one UDP datagram, and this datagram is delivered to the IP layer, and then it is up to the IP layer to apply fragmentation on this big message, on this big datagram, so that it will be divided into small pieces, small chunks, small packets, and in the end, on the other endpoint, these pieces will be put together again and delivered to the UDP transport layer.
So I have a question.
Sure.
If there is a fragmentation, it's not important if the messages don't arrive in the right order then?
Sorry, say that again.
If there is a fragmentation,
yes,
the different messages may not arrive at the end in the right order. It's
correct.
Not important.
Correct. And this is up to the IP layer to handle this. So this is transparent to UDP.
Okay.
So when you have a big datagram that is delivered to IP will fragment this datagram into smaller packets. These packets will be put in order to recover the whole datagram. So if IP is able to recover the whole datagram, the datagram is delivered to UDP. Otherwise, it will be discarded.
Okay, thank you.
Most welcome. And again, so it is also related to this question, UDP does not preserve the order of the data of the messages that are sent by a given destination. So they might arrive out of order to the destination. Now, I will explain the interface between the application layer and the transport layer. So remember the example that I gave last time. So where you wear the application, you have a postcard to send to a friend, and your transport layer is the post office. And the interface between you, the application, and the post office, the transport layer is the counter. So whatever you need is you need to do with the transport layer, you should go through the counter, and this is the only interface that you use. And with the transport layer and the application, the interface that you have, actually it is a programming interface, and it's called socket. So whatever you need to do with the transport layer as an application, you need to go through the socket to communicate with the transport layer, to interact with the transport layer. And here we explain the socket, the UDP socket. So how to interact with UDP. First of all, so here we call it socket interface. So it is a socket library that is available with many languages like Python, Java, C++, and all these libraries have the same behavior and almost the same syntax. Why? Because they interface with the lower socket library, with the lower socket library of the operating system. So actually, when you create a socket here on Python, for example, this socket will call a lower level library. So it will call the lower level library of the operating system to create a socket at the operating system level. So what we describe here, applies on almost all library sockets of the different object-oriented programming languages. And in the lab, we'll see this in more details. We give you examples, and also we'll be able to write your own application to interact with the sockets, and it will be in Python. Now, on the server side, the first thing we need to do is to create the socket. So we call this socket, and inside this method, this function, we indicate the type of the socket that we would like to create. In this case, it is a UDP socket, and this method returns a file descriptor. It's just a number that identifies the socket. Then, since given that is a server, so the server should be listening on a well-specified port number. So this is done by the function bind. So when we call the function bind here, so we are binding this server to listen on a given port. But also we can bind the server to listen on a given interface and port at the same time, because now almost all machines that we might have more than one interface. So let us think about your laptop. You have one Wi-Fi and one wired interface. So with the function bind, you can specify whether you would like to listen all interfaces that you have, or on only one of these interfaces. And when you are bound to the local IP address and local port number, you can start listening to receive incoming requests. And this is done by receive from. So receive from is a blocking function. What does this mean? So it blocks until it receives something. By default, it's blocking, but there's something that we can change using some socket options. But by default, receive from is a blocking function. So this means that the program will arrive here and will block until there's some available data in the buffer of the socket. And receive from returns two things. The first thing is the data. The second thing is the address of the socket that's sending this information. So this means that it will return the data and the IP address and the port number of the application that's sending this data. Now let's go to the client side. So here we create a UDP socket. It's exactly the same thing as creating the socket with the server. And then once it's created, we don't need to bind it explicitly to a local port, because it's done automatically but by the language, by the socket library. But the socket library actually chooses a random port number and bind the socket to this port number. But if we want, we're still able to specify a port number and apply the bind method on this socket. But by default, it is a random port number. And then once it's created, we can start sending data. And again, with this send to method, so this takes two arguments. The first one is the data we need to send, and the second argument is the address of the application. And this address actually is formed from the IP address of the server and the port number on which the server is listening. So the address is the remote IP address and the remote port number. And that's it. And then once it is the data is sent, so we can either close the socket because we are done, or if the application has more data to send, we can go back and send more data as we want. Now we need to be careful about one thing. So with this client, with this socket, we are able to communicate with many servers at the same time. So we don't need to create one socket to communicate with one server. So all what we need is to precise the remote IP address and the remote port number inside the send to message. So with the same socket, we can talk with server 1, server 2, server 3, and all what we need is to distinguish between these servers is to indicate the remote IP address and the remote port number of the server that you would like to communicate with. And here we see, for example, how to execute these two programs. Here we execute the UDP client. We gave the destination address of the server. So and here we provide a message to send to the server. For example, just a toy example of a program that could be a client. And then the client will take this message, will send this message to this IP address on a hard-coded port number inside the program, and the message should be received by the server if it is running. At the server, so we can start the server by this comment, for example. But here there's something that I don't really like pretty much, because we show the client before the server, as if we say, okay, we can start the client and then we can start the server, which is wrong. So first we need to have the server running and listening to the port number, then we can start sending the data to the server. So here, how the socket is seen by the operating system. Just to give you a mental image how the socket interacts with the layers beneath. Here we have different sockets. Every socket is identified by its file descriptor. So here you have an application that can interact through this socket to send data. Behind the socket, we have a buffer. Why we need the buffer? Because when the application needs to send some data, the operating system might be busy doing or serving other processes. So this data should wait in some place, otherwise it will be lost. This is why we have this buffer that's just beneath the socket interface. So the data will go from the application. It will be stored in the buffer, and again, this is associated to this port number. And when the operating system is ready to serve this socket, so that the data will be sent through the associated IP address. And on the other way, so when the IP layer receives a packet, so the packet will be delivered to the UDP. The UDP, based on the destination port number, will dispatch the packet to the right application. So if the destination port number is 32456, the packet will be delivered to this application. It will be stored in the buffer because the application might be busy doing something else. So this data will wait in the buffer until the application is ready to pull this data from the buffer. So here we have two sockets that are associated to the same interface. Here we have another socket that is associated to a different interface. And all of these sockets are listening to different port numbers. Now we move to TCP. TCP is much more complex actually than UDP. First of all, we'll start with some basic operations of TCP. Through this very simplified diagram, we'll show some properties of TCP. The first property is reliability. The second one is in-order delivery. The third one, unit of information, is byte and not a message like with UDP. And also, we'll see a new feature that we didn't describe last week. It is the flow control. What is missing in this diagram is the congestion control, which actually requires a full session to explain it. So this is why we don't show it on this diagram. But again, this diagram is a very simplified version of TCP operations. Now we have A is sending data to B. So it's sending 500 bytes, but these bytes are numbered. So they're numbered from 8001 to 8500. And this number actually is the number of the next byte expected to send. So the length of the data, the number of bytes that are sent is just the difference between this number and this number. And at the same time, A is acknowledging the byte 101 that has been already sent by B. So B has already sent some data, and now A is acknowledging the data that are received by A from B. And what does this mean, acknowledge 101? So the acknowledgement with TCP is cumulative. This means that all bytes that are received before 101 are well received. And now the next expected byte is the byte number 101. And also, A sends what we call a sliding window of 6,000. This means that A is able to receive up to 6,000 bytes before having a buffer overflow. So this is a way to control the throughput between A and B in a way that both ends are able to handle the data that's sent. So if B sends more than 6,000 bytes, A will encounter a buffer overflow and the data will be lost. It's why so A is telling B, please don't send more than 6,000, otherwise we'll have to retransmit the data that will be lost because of the buffer overflow. So now this data is well received here, and they put this data in the buffer to be delivered to the application, because they are ready for delivery to the application, because they are in order and everything is going well. So there's no reason to let this data wait. So whenever the application is ready to pull data from the socket buffer, so this data will be pulled and delivered to the application. Now, B receives this data, it acknowledges the received data and sends more data from its side. So now it sends 100 bytes numbered from 101 to 200. It acknowledges the next expected byte. This means that now all bytes before this having numbers below this number are well received, and the next expected one is 8,501. And the windows, the sliding window is 14,000. This just to tell A, please don't send more than 14,000. Otherwise, I will have buffer overflow. So this is what we call the flow control. It's end to end. It's based on the conditions of the two endpoints of the communication, and it's completely independent of the conditions of the network. Now A sent another packet, 8,501 till 9,000. It acknowledges the received data from B and it updates the sliding window. This packet is lost, but A is not aware about this loss. It continues sending new data. Now B at this point, it will look at the numbers it receives. It will see that there's something wrong, because what is expected is the one that was lastly acknowledged, which is 8,501, but what B receives now is 9,000. So this means that there's something wrong. So what it does, it simply just it sent an acknowledgement just to remind A, or just to say to A, be careful, I am still waiting to 8,501 that I have not received this byte. A continues sending data. B again send an acknowledgement only for 8,501, and it sends some data from its side to A. And the data that has been received from these two packets cannot be delivered to the application, because if they are delivered to the application, this will create some out of order of delivery of data to the application. So they are put in some buffer, just waiting for the lost data to be recovered before delivering them to the application. Now, at A side, so whenever A sends a packet, it sets a timer. So if there's no acknowledgement for this packet that arises before the expiry of this timer, so the A will retransmit this packet. And this is the case here. So we have a timeout. And now for A, the packet is lost, and it's time to retransmit this packet to B. So it retransmits the packet, 500 bytes, then the missing numbers. It acknowledges again, it acknowledges also the last byte received from B, and it updates the sliding window. So now B can put all this data together, and the data can be delivered to the application. So they will be so B will put this data in the buffer of the socket, so that the application can pull this data whenever it's ready to do it. So B acknowledges the received data. Now A, for some reason, it was waiting just to be sure the data is well transmitted. Then it can continue sending data to B. Now, as you can see, TCP is very complex compared to UDP. With UDP, we don't have all this mechanism. UDP, it sends the data and that's it. We are done. So the mission is accomplished. And this is why with UDP, one socket can communicate with many servers, because it does not need to maintain any state of the communication, any information about the communication. So, but with TCP, what we do, we need to maintain some information about the number of bytes that are sent, the number of bytes that are received, what are the timer state right now. We need to set to fire a timer every time we send a packet. So we had a lot of things to do in order to maintain the good communication between these two endpoints. So this is why with TCP, one socket cannot communicate with many sockets. So one socket should be connected to only one remote socket. This is what we'll see next. And also, I would like just to emphasize something. Last week, we talked about head of line blocking. And this is exactly what's happening here. So here we have head of line blocking because this packet is lost. So this packet should wait, cannot be delivered until this packet is recovered, this loss is recovered. And this is what we call the head of line blocking. Now, TCP socket. The interaction with the TCP socket is very easy. So all this complexity that we have just seen is hidden to the application. So TCP writing to TCP socket or to UDP socket is exactly as if you are writing to a file or reading from file. And all the complexity that's beneath the socket is hidden to the application. And this is the good thing of this interface. First of all, let us look at the client side. So on the client side, we need to create the socket the same way we create the UDP socket. So all what we need is to indicate here that is a TCP socket. So it is a stream socket actually. And now once we create the socket, before being able to communicate with the remote server, with the server, we need to connect this socket to the remote socket. So because one socket cannot talk at the same time to many servers, it should be connected to one socket so that they can exchange data. How this happens? Let us look at the server side. So we create the socket. We indicate here that this is a TCP socket. Then we bind the socket to a local remote, to a local port number. And if you want, also we can bind it to a local IP address or interface. Once the socket is bound, we call the listen. So the listen function, it is not called with UDP, it's called only with TCP. Why? So listen will create a queue for incoming request to connect. And then after the listen, after creating this queue for incoming requests to connect, we can start listening for incoming requests to connect, for incoming sockets that needs to communicate with the server. And this is the role of the accept. So once the accept method, actually, again, it's by default a blocking function. So it waits until it receives request to connect. When it receives request to connect, it will create a new socket. So actually it's a socket, it is a connected socket. And what does this mean? So because when accept, okay, let's just be careful about this, is very important. So accept returns a new socket. This means that now we have two sockets. We have S1 and con socket. So what we need two sockets, actually, this new socket is created to communicate with this client because this client send a SYN packet to the server S. So the server S will acknowledge the SYN packet, and then the client will acknowledge the acknowledgement. And once this handshake is finished, so the accept returns and create a new socket, and the communication between the client and the server will be from S here to con here. So S1 does not participate in the communication between the client and the server. S1 is here just to establish the communication, to create a new connected socket between the server and the client. So the difference between S1 is bound to the local IP address and local port number, but connected socket is bound to the local IP address and the local port number, but also to the remote IP address of the client and the remote port number of the client. And this is this socket which is able to communicate, to exchange data with the client. But the first socket is here just to establish the connection with the clients and to create a new connected sockets that are able to exchange data to communicate with the client. So, and now the communication between the client and server start between point 1 and point 2. So here we create the connected socket. Here we have the handshake to create this connected socket, and then the data, the application data, can be sent between point 1 and point 2.
I'm sorry, does that mean that S1 can work in parallel to?
Exactly, yes.
Okay.
That's what we'll see in the next slide. Exactly, yes. So now we have two sockets, and this will be explained here and in the, also again in the coming slide. So point 1, point 2, we have now two sockets, one connected, one non-connected. The connected one will continue communicating with the client. So here we have send, we have receive, and just notice this difference between TCP socket and UDP socket. With UDP socket, we used send to, because with send to, we gave as argument the data, and we indicate the server to which we want to send the data. With TCP, we don't precise to because it is connected. So it's by default, it's not only by default. So the socket cannot communicate with other socket than this one. So all what we need to do is send, and we deliver the data to the function send. Now the data received to the server, and then if we have more data or we are expecting some reply from the server, we can call send receive or whatever, and once we are done, we can close the socket. The same thing here, so connection receive, we receive the data, we apply some processing on this data, and then if we are done, we close the socket and we go back to listen for new incoming request to connect. Now, but it's not efficient, because with this diagram, we can serve one client at once. So we cannot serve many clients at the same time. So we need to finish from serving the first client to be able to take another client, to connect it, to create a new connected socket so that we can establish the communication. So it's not efficient at all. So what happens usually is that, so once you create, when you have a connected socket that is created, so you fork a new thread and you deliver the socket identifier to the new thread that will handle the communication with the client, and then you go back directly immediately to the accept method that will be wait for other incoming requests to connect. And that way we can serve as many clients as you want in parallel. So this means that we have one non-connected socket which is bound to only the local IP address and the local port number, and we have as many as we want connected sockets that are bound to the local IP address and the same port number, but also they are bound to the remote IP addresses and the remote local numbers. To the remote port numbers. So to answer the question, yes, we have many sockets at the same time listening on the same port locally. S1, non-connected, is not able to communicate with the client. It's here just to create a new connected socket. And we have connected sockets that are bound to the local port number and to the remote port number and IP address. And every socket can communicate with only one client. With only one client. And these are connected, and S1 is non-connected.
Excuse me?
Yes?
These are for different clients, each one, or for the same?
For different clients. Here I show only one client, but actually every socket is connected to a different client. So this one is client 1, this one client 2, client 3, client 4, client 5. So as many clients as you want, but one socket can communicate with only one client.
And then the sockets are different, right? Every socket is different.
Exactly, yes. So here, all of them are connected. Actually, it should be con1, con2, con3, con4, etc. So we have many sockets. Every socket has different name for sure, and every socket communicates with one different client.
And in UDP, we don't have this.
UDP, we don't have this. UDP, we have only one socket here, and this socket is able to communicate with many servers at the same time. All what you need to do is to indicate the IP address and the port number of the server, and that's it. And instead of send, it is send to. With send to, you have the data, and you have the address of the remote server.
Okay, thank you.
Most welcome. Now again, the operating system view of TCP sockets. So here we have the non-connected socket. Here we have the buffer for incoming request to connect. It is bound to this port number. Here we have connected socket. So here we have connected socket. So every socket is bound to the local IP address and port number, and to a different remote IP address and remote port number. This is why we call them connected socket, and both of them are associated, bound to the same port number as the non-connected socket. And here we can see that in this case, for example, they're associated or bound to one IP address of the local machine. Paul, question. S sends a message to D with a size of 2000 bytes. D performs a single socket call receive from, which is true. So D receives 2000 bytes only if S uses TCP. D receives 2000 bytes if S uses UDP. D receives 2000 bytes irrespective of TCP or UDP. None of the above, I don't know. So what do you think? I will close the poll in 5 seconds. I will close the poll. Share the result. And the majority is correct. The right answer is 2. Why? Because with UDP, the message delivers the data to UDP, and UDP takes the data as it is and send the data to the other endpoint, to the destination. And in one received from the application should be receive the data as it was sent. So if the source data delivers 2000 bytes, the destination data will receive 2000 bytes. With TCP, it's more complex than this. So with TCP, the data might be segmented, and the size of the segment depends on the control flow, on the flow control mechanism that we have, on many things, and the unit of information with TCP is byte. It's not a datagram. It's not a message. So the TCP can do whatever it wants with this 2000 bytes. It might send them in one chunk, or it might send them in small pieces. It depends on the conditions of the operating system or of the other endpoint. So we are not sure whether this will be delivered as one chunk to the other endpoint with TCP, but with UDP, we are sure that the packet will be sent as it is delivered to the UDP. It will be received the same way it was by the destination application.
Sorry, I have a question.
Sure.
So it could send many sockets for TCP in the case of TCP.
What do you mean?
It will create many different parallel sockets to
It is-
send this
It
2000
is up to
bytes?
the application to do it. If the application decides to create different sockets and sends a piece of data through every socket, it can do it. Yes.
And this is the application who decides so.
Exactly, it's the application that decides to create many sockets. So it's not the socket. The socket
Okay.
is only one channel, one TCP channel, the socket. If the
Okay.
application has many files to send to the destination, so the application can create many sockets at the same time and send one file through one socket. So in parallel, it can send many files through the many sockets that it creates.
And this file of 2000 bytes could be divided in a lot of files.
In a lot of segments.
Segments that could
Yes,
be
and in the end, this will
sent-
be, sorry?
It will be divided in a lot of segments that could be sent into the different sockets that were created, or not?
No, actually, when you deliver 2000 bytes to a TCP socket, so these 2000 bytes will go through the same socket all the time.
Okay.
But TCP might segment these 2000 bytes. So instead of creating one segment with 2000 bytes, it might create one segment with 500 bytes the first time. The second time, it might send only 700 bytes. And the third time, it might send the remaining.
Okay.
And the other side, it is up to the application to put all this data together. So this means that both applications on both endpoints of the communication should agree on some protocol so that they can recover the data that is sent through through a TCP socket.
And it is a single TCP socket.
Now, yeah, I'm talking about a single TCP socket.
Okay, perfect. Thank you.
So that's the difference between TCP and UDP. With UDP, the data will be sent as it is delivered by the application. So if the application delivers a message of 2000 bytes, so the size of the UDP diagram will be 2000 bytes.
Okay, thank you.
Okay, so I think now it is the time to break, and we resume in 14 minutes.